Today we're going to look at the Combined Science Physics Paper 2 and the higher tier paper. First question is all about waves, and we're looking at a longitudinal wave. This question is nice to you because it's giving you the choices of what to look at. Here this could be something like a sound wave. You need to identify A and B. If you look at A, this is where the particles are spread out. We call that rarefaction. Then the second part is B. It's a point between two waves. In this case, it's the same point, or the corresponding point on the next wave along. That is the wavelength. It is well worth revising both your longitudinal wave and your transverse wave and making sure that you can label them. These questions come up all the time. Right, now, the wave shown in figure 1 that we just looked at has a frequency of 4 kilohertz. You need to calculate the period of the wave. You need to use a physics equation sheet, and you need to give your unit. Now, there's lots of marks available on this question, 4 marks. So this is telling you that you're going to get 1 mark for giving the unit. Now, bearing in mind that the formula at the time period equals 1 over frequency, this is really generous for for the other 3 marks. So you should be getting a little bit suspicious, and this is a bit you need to be suspicious of. 4 kilohertz. The first thing you need to do is to convert that 4 kilohertz into hertz. That's our unit of frequency. We multiply by 1,000. So that is another mark. Well, that's our first mark gained. We've done the conversion. We now substitute our numbers into the formula. So we need to work at the time period. So it's just T equals 1 over the frequency of 4,000. Now put those numbers into your calculator, and then you just need to carefully read off the numbers, which is 0.0025. The unit is going to be in seconds. So you can just write a lowercase s. Remember, it's a time period. In physics, we always measure things in seconds. And there's your 4 marks. Now, sound waves are longitudinal. That was probably a picture of a sound wave that they showed you before. Now, figure 2 shows how the speed of sound varies with the temperature of air. 1.3 should be the easiest mark you're ever going to get because you're going to have the formula sheet. So, wave speed, V, is frequency multiplied by wavelength. There's your 1 mark. That sign is lambda, one of the Greek letters. Now the next question, we're going to have to use those numbers, or we're going to have to use that formula to calculate. In this case, it's the wavelength of the sound wave. So the sound wave has a frequency of 300 hertz. Now we need to work out the wavelength. Now again, lots of marks available, 4 marks. Well, we've got the formula in the question above. Now, this is where we need to use the graph, because there's a clue here. We're talking about the air has a temperature of 28 degrees centigrade. So we need to use the graph to calculate the speed of sound. Once we've got the speed of sound, we've also got the frequency, we'll be able to determine the wavelength. So you need to read off the scale. We need to find 28 degrees, which each small square is worth 2 degrees. So it's 1 small square down from 30, and you're going to use a ruler. It's much easier for you to do it than it is for me on here. And then we draw across, and on the graph that should come out as being at 348 meters per second. So we've got our formula: V, speed of the wave speed, frequency multiplied by wavelength. We've got our velocity off the graph, that's 348, equals frequency, told it's 300 hertz, multiplied by our wavelength. We need to get the wavelength by itself, so to get lambda, the wavelength, equals 348 divided by 300. that is going to give you an answer of 1.16 meters. Well done if you got that question, that part of the question right. Again, it's a nice 4 marks to get. That total question is out 11, so well done if you got all 11 marks. Right, the next question is about the wheelchair competitors racing at the London Marathon. Now, for this question, it's telling us that the distance of the London Marathon is 42,000 meters. Now, 2.1, it's again another easy mark. We need to write down the equation that links distance, force, and work done together. You've got the formula sheet. Now, work done is force times distance. Now, I know it can cause confusion, but the letter S represents distance. If you're not comfortable with that, just write out the words. Either way, you'll get the marks for this. Now, 2.2, we're going to use that formula. So during the race, competitors work against air resistance. So the work done against air resistance by the winner of the race was 3,360,000 joules. So we're being told, it's worth highlighting, we've got the work done. Remember, we've got the distance of the race up here. We're going to need to use that. We need to calculate the average air resistance acting on the winner of the race. So there's a clue that we need to use that formula. Work done is force times distance. Well, we've got the work done value, so we'll substitute that in. So quite a big number. Force, F, is what we need to find. And that's going to be multiplied by the distance, which is 42,000 meters. We now need to make the force the subject of the equation. We need to divide both sides by 42,000. That is going to give us F equals 3,360,000 divided by 42,000. Make sure you put these numbers carefully into your calculator, and that should give you an answer of 80 newtons. With this, it's very easy to put too many zeros or too few into your calculator, so you need to be really careful with this bit. Okay, question 2.3. Which equation links distance travelled, speed, and time? Again, you've got your formula sheet to look at. Distance travelled is speed times time. Again, should be another easy mark. And then for question 2.4, we just need to use that formula. So you've got distance equals, well, I'm just going to write V for speed, multiplied T for time. We just need to substitute in the numbers that we've got. So we've got the distance, and it's telling us again it's 42,000 meters. We've got to work out the average speed, which is V, multiplied by 5,600 seconds. Again, we're given the value in seconds, there's no conversions needed here. We just need to get V by itself, speed. So V equals 42,000 divided by 5,600. Put those numbers into your calculator and you get 7.5 meters per second, which is quite quick for a marathon. And then 2.5, we need to try and explain why the speed of a competitor changes during the race. Now this is where you just need to think about it. I'm sure none of you use a wheelchair, however most of you probably ride a bike. And you need to think about, if you had to ride around that marathon course, what would affect your speed during the race? Well, at the start, the competitors are stationary, and then of course the gun goes off and they accelerate immediately. So you're going to accelerate, speed up at the start. Well, that means your speed goes up. And this question really is about common sense. The other thing to think about is, again, you're riding your bike, the road isn't flat. So the road is not flat. So what happens when you come to an uphill? Well, if there's an uphill, your speed is going to go down. So you're doing work against gravity. If you're going downhill, all the best bits, your speed is going to go up. And then you probably find that you need to slow down, so your speed goes down when you're going around corners. So that will affect your speed. Also, in this case, these wheelchair competitors are travelling 42,000 meters. That's 26 miles. They're going to get tired. So they get tired. When you get tired, well, your speed is going to go down. Also, again, think about if you're cycling, things like wind. The wind's direction may change. So the wind is an example of a resistive force. So the resistive forces, the wind, may change during the morning of the day of the event. So if you've got a tailwind, your speed's going to go up. If you've got a headwind, your speed's going to go down. Again, it's another point to make. The other one, and again relate this back to your cycling, you might get a puncture, and again that just adds to the resistive forces, and that would affect your speed as well. So you just need to make those points to get the 4 marks, and just put it into a logical order. Talk about what is happening, and then remember to relate it back to, therefore this happens to the speed. Okay, now we're on to question 3. This question is all about momentum. And we've got a child playing with a toy, and the train is on a bridge. And when the child lets go of the train rolls down the bridge. We're given the value of momentum in this question. We've got the mass of the train is 180 grams. We need to calculate the velocity of the train at the bottom of the bridge, and it's asking us to use a physics equation sheet. That makes life easier because obviously you've got all the formulas there. Now again, you should be a bit suspicious. This is worth 4 marks. We're just using one formula, which is momentum, which is represented by P, is mass times velocity. We're getting 4 marks for doing that. So again, be suspicious, and the mass is what you should be suspicious of. We've got 180 grams. We need to convert that into kilograms, so we need to divide by 1,000. That gives us 0.18 of a kilogram. There's a bit of a clue in the units for momentum. The fact that the units of momentum are kilograms meters per second. So again, just be suspicious when they're being very generous with the marks like this. We now just need to substitute our numbers into the formula. So we've got a momentum of 0.216 equals our mass, which we've now converted to 0.18 of a kilogram, multiplied by velocity. We then need to solve that equation. So we need to get v by itself. So we divide both sides by 0.18, which gives us 0.216 divided by 0.18. If you put those numbers into your calculator, you're going to get the value of 1.2 meters per second. Nice 4 marks to get. Okay, now on 3.2, need to know a little bit of science now. So the train collides with a stationary carriage on the track. Explain why the velocity of the train after the collision is less than it was before the collision. You need to use ideas about momentum in your answer. Well, the first key bit about this is that the total momentum is conserved. So that means all the momentum that was there before the collision is carried into what happens afterwards. Now, before we have the collision, the train is moving, so that will have a momentum. However, a carriage, a stationary carriage, won't have any momentum before the crash because it's stationary. Remember, momentum is mass times velocity. If it's not moving, the velocity is 0. Multiply anything by 0, it means it has no momentum. Now, the train crashes into the carriage, so during the collision, the momentum of the carriage increases because the train hits it and it makes that carriage move. Now, this means, therefore, the momentum of the train is going to go down because anyway, some of that momentum has been transferred to the carriage. Then, because momentum equals mass times velocity, it means that the velocity, the v of the train, has to go down. So it decreases. So in terms of where do we get the marks from here? So we get your first mark for talking about momentum is conserved. During the collision, momentum of the carriage goes up. There's our second mark. Our third mark comes from the idea that the momentum of the train therefore goes down. And then the final mark, the fourth mark, is by linking this to momentum is mass times velocity. Remember, the mass of the train hasn't changed, so it means that for the momentum of the train to have gone down, it must be the speed, the velocity of the train decreases. And that's where your fourth mark comes from. Well done if you got all four on that one. Alright, number 4, we've got an example of the motor effect here. So figure 5 shows you the equipment used. First bit, explain why there is a force on the wire when there is a current in the wire. Now remember, there's a magnetic field with our magnets, with our permanent magnets. So we have a magnetic field, and then the current flowing through the wire also produces a magnetic field. And it's that combination which causes there to be a force on the wire. Now question 4.2 is asking you to explain how the direction of the force on the wire can be predicted. So this is the bit where you need to be using Fleming's left hand rule. Now you need to remind yourselves about this because the Fleming's left hand rule comes up a lot. So if you remember, the thumb is going to be the direction that the wire moves in, so that's the direction of the force applied. Your first finger needs to be lined up with the magnetic field lines. Your second finger is lined up with the direction of the current, so the direction of the current. Now if you do that, and from that the thumb gives you the movement. Now you would get a mark if you actually said that the force on the wire would send it downwards. So you can actually do this with your left hand. So you had the magnetic field line, it goes from north to south, but the current was travelling the other way. So this is where you need to be a bit of a contortionist. It's probably quite hard to see on the camera there, but my thumb is now pointing down. I'm trying to put it so that you can see it. It's quite a tricky one to get your hand to move in that direction, but you know, use the left-hand rule. Make sure you're using your left hand, which is probably a bit easier for most of you. You're right-handed. You've got your pen in your hand. You're using your other free hand to work this out, and your thumb points in the direction of the force applied on the wire. And like I said, in this particular case, our wire will move down. And then 4.3, we're given an example of a simple electric motor. we need to explain one way that the motor could be changed to increase the rate at which the coil rotates. This one's a nice question if you get it. Here we've got, you've got your coil of wire. This is the key bit in this particular question. You've also got your magnet right here. How do we increase the speed or increase the rate at which the coil rotates? Well, if we increase the number of turns of wire in the coil, so we're increasing the magnetic field induced there, or we could increase the current in the coil. So we could use a cell with a higher potential difference, so we could use two cells and make it into a battery. Or, third option is to use a stronger magnet. Again, make the magnetic field stronger. Now, any of those three answers would give you the first mark. The second mark comes from explaining what the effect would be, which the effect would be any of these things would increases the force on the coil due to the motor effect. And there's your second mark. So remember, we need to be explaining one way. So it doesn't matter which one, which thing we pick on, we then need to explain why we've done it. Essentially, we're increasing the force due to the motor effect. With question 5, we've got a student investigating how the colour of a surface affects the amount of infrared radiation that the surface absorbs. And you've got a diagram of the picture used, and we've got two flasks that are painted different colours. You've got your black flask and your white flask. And you're given the method, and we need to come up with two improvements to the method that the student used. So, pretty quite apparent straight away that the two lamps are at different distances from the infrared lamp. Straight away, that's no longer a fair test. So we need to place the flasks. So place flasks at same distance from the lamp. And of course we need to explain these changes so that the intensity of the infrared radiation is the same. That's very much one of our control variables. The second one, you've got to make sure that the flasks are the same size and shape. So use same size and shape of flasks, and this means that they've got the same surface area. So again, it's just another control variable. So that surface area of which can absorb the infrared is the same. They're probably the two obvious ones, but the other one is make sure that you're using equal volumes of water in the flasks. That's not obvious whether they're doing that or not, but we need equal volumes of water in the flask, because of course the more water you have, the slower the temperature rise. 5.2. Here we've got a graph showing the results for each flask, and we need to complete the sentences. So after 100 seconds, the temperature difference between the black flask and the white flask was how many? Well, we need to find 100 seconds on our graph and mark those parts there. And if we look at the graph, it works out as being, that's 24 seconds. I would say that is about 31.5. It's really a lot bigger on the printout of the graph that you've got. And then all you need to do is 31.5 minus 24. That will give you 7.5. And then the second sentence, the temperature of the white flask stopped increasing. The temperature inside the black flask continued to increase for a further how long? And again, we're now just looking from when the graph went kind of flat. So So that is around about 200 seconds here for the white flask, and if you read carefully, it comes out as 440 seconds for the black flask. The difference, 240 seconds. 5.3. The initial rate of absorption of infrared radiation by the black flask was greater than the initial rate of absorption by the white flask. How does figure 8 show this? Well, we should be looking at the gradient, and the black flask gradient is much steeper. So black flask gradient is steeper. Remember, we're looking at the rate of how quickly these are warming up, therefore we're looking for the steepest part of the graph. Now 5.4, explain why the temperature of the water in the flasks increased and then became constant. Now this is important, so you've got 4 marks to look at here. Now it doesn't matter whether you're talking about the black or the white flask, the actual answer is the same. So the flasks initially absorb infrared IR radiation, and they also transfer some energy to the surroundings. So it's important to remember that not only do our flasks absorb infrared radiation, they will also emit some of that energy to the surroundings. Initially, the rate of absorption of infrared is going to be greater than the energy, I'm just abbreviating it to E, than the energy transferred to the surroundings. So that means that next, the rate of energy transfer to the surroundings increases as the flask gets hotter. And that's until the rate of energy transfer to the surroundings equals the rate of energy, or the rate of infrared absorbed by the flask. At that point, temperature stays constant. So you just need to sort through that in a logical way, and that's where you're going to get your 4 marks from. To question 6, the distance of a car travelled during the driver's reaction time is called the thinking distance. Now we've got a graph showing how thinking distance depends on the speed of the car, and we need to determine the driver's reaction time. So remember, we need to be using the equation distance is speed times time. Remember, distance is represented by the lowercase s, and we just need to look for some values to put in. Well, because this is a straight line, it doesn't matter where on the graph we pick, but we might as well go for the big numbers. So this top point here shows that we have a time of 30 seconds, and we have a speed of 21 meters per second. So we're just going to substitute our numbers in. So 21 equals our speed of 30 multiplied by time. We don't know what t is. Just need to rearrange that. So t equals 21 over 30. Put those numbers in your calculator and you get 0.7 seconds. Nice little question to start with. A fairly straightforward 3 marks if you remember to use the graph properly. Now 6.2, we've got another graph, and it shows how the velocity of the car changes during braking. and we need to determine the braking distance of a car. Now the important thing to remember here is that the area under the graph of a speed time graph or a velocity time graph tells us distance travelled. Now they've given us these nice big squares and we need to count those squares, but first of all we need to remember that 1 square equals, well, it's 1 times 5. So each square means 5 meters travelled. So I would go through this with your pencil and just try and work out, and it's almost in some cases having to guess a bit. So we've got 1, 2, 3, 4 fairly intact squares there. I would put those 2 bits together to make 5. The top 2 bits, that one and that one, pretty make 6, and then put that and that together would give us 7. You've probably got that and that make 8, and those 2 bits make 9, and we have 9 squares underneath the line. And then it's a case of distance travelled, distance equals 5 times 9, and that gives us a braking distance of 45 meters. Really, this question is just the key bit is remembering that the area under a speed time graph tells you the distance. Right, 6.3, explain how the gradient of the line on figure 10 shows that the resultant force on the car was not constant. Well, the gradient of the graph represents the acceleration. Well, the gradient is not constant because it's a curve. If it was a straight line, it would have been constant. However, in this case, we've got that curve, which means it's not. So that means that the resultant force can't be constant. And that's because, and this is linking this to F equals ma, force is proportional to acceleration. Okay, that question's out of 9 marks. Well done if you got all 9. Okay, question 7, we've got figure 11, which shows a stationary apple hanging from a tree. X marks the centre of mass of the apple. Draw 2 arrows on figure 11 to show that the forces are acting on the apple. Now here you've got an advantage because you've got a ruler. Here we're just going to have our first arrow, which disappeared, and our second arrow is going to be going in the opposite direction, but it's going to be of equal length. So equal and opposite forces, the apple isn't falling, so the forces should be balanced. Right, this next question is great, and it is one of those where you're going to be needing to use 2 formulas. So if it takes half a second for the apple to fall to the ground, the initial velocity of the apple is 0 meters per second. Acceleration due to gravity is 9.8 meters per second squared. We need to calculate the distance fallen by the apple. Now, this one, when we're talking about a time there, we've got an initial velocity, we've got an acceleration, calculate the distance. This is where we need to be using our v squared minus u squared equals 2as formula. Now, the only problem we've got is we don't know the final speed of when the apple hit the ground. Now, what we do have though is we've got the acceleration, we've got the initial velocity, and we've got the time that it took for the apple to fall. So we can use, well, first of all, we need to use the acceleration is change in velocity over time. Now, change in velocity is final velocity minus initial velocity over t. So we now need to substitute our numbers in. We've got an acceleration of 9.8 equals v minus, well, the initial velocity was 0, that makes it a little bit easier, divided by 0.5. We need to get v by itself, and we end up with our velocity of when the apple hit the ground of being 4.9 meters per second. We now need to go back to our original equation and just substitute in the numbers that we've now got. So we've got 4.9 squared minus 0 squared equals 2 times 9.8 multiplied by s, which is the distance, which is our unknown. And then we just need to start multiplying this out, so we end up with 4.9 squared equals 19.6 s. Just get s by itself, so divide both sides by 19.6, so that's going to be 4.9 squared divided by 19.6. When you put those numbers into your calculator, that comes out with a nice even number of 1.2 meters. That's a great question. It's worth 6 marks. Not a huge amount of writing to do, however, it's using the two formulas, so you need to get comfortable doing that. And then the final question. In the previous question, it was assumed that the acceleration was a constant 9.8 meters per second squared. Evaluate this assumption. Well, in this particular case, there's two possible answers. Now, we can take the approach that this wasn't a good assumption because as the apple falls, air resistance increases or starts to increase. So of course we start accelerating, air resistance will start to build, and therefore the resultant force on the apple will go down. If the resultant force is decreased, it means that our acceleration also decreases. That means that the acceleration will not be constant. Will not be constant, which means that therefore this is not a good assumption. So that's one version of that answer. You could go on the other side, where you think that it is a good assumption, because the apple only falls a short distance. So it means that air resistance is minimal or negligible, virtually zero, negligible. So it means that the resultant force is constant, which means, because of course F is directly proportional to acceleration, it means that acceleration is also constant. Therefore, this is a good assumption. Now, in that particular case, it doesn't matter which way you go, whether you say it is a good assumption or a bad assumption, as long as you're making those points, you'll get the full marks either way. You're now at the end of that paper, so that question was out of 12. Count up your score, and then of course the whole paper is out of 70. So well done if you got 70 out of 70.